way we look at the way we process the MAC and the phi layer. So by thinking about it slightly differently, we created a bit interleaved PON called BiPON technology. It was announced. I invite you to go to greentouch.org, look at the website, look at the papers, look at the technologies, see where you can fit in. But GreenTouch has the official goal of improving the energy efficiency of networks by a factor of 1,000. Now realize that over the last 10 years, energy efficiency of networks has been increasing by about 20% per year. So over 5 years, this would be about a factor of 2. Prior to GreenTouch, most of the most ambitious research programs on the planet were going for a factor of 5. GreenTouch is going for a factor of 1,000. This is addressing the problem at the most fundamental limits, addressing some of the most fundamental questions in networks today. With active participation, we meet face-to-face twice a year. Our next meeting is in Dallas, Texas, is in June. I welcome everyone here to come participate in that. These are not nice research conferences in Hawaii or exotic places with great city tours. These are real science working groups, some of them going well past midnight, discussing, debating, arguing different approaches and different perspectives of this problem. Here's a list of some of the research projects, some of the leaders of these projects. And again, GreenTouch is a global consortium. But one of the most interesting pieces is that the largest membership, if you look at the constituency of GreenTouch, the largest membership comes out of the APAC region, Asia Pacific region. So there's a huge participation in this side of the world. And then, of course, in Europe and the United States as well. But there's a very active research community here in APAC. So let me just spend the remaining time going through the wireless side of the equation. While there are contributions from everywhere, wireless, as I said, is the most inefficient access technology, and the physics of that is pretty straightforward. Just take a look at a cell. You have a base station. As you can see, the base station consumes the most power over all the other components of a network. So base station is big. It has a big power amp because it radiates many, many hundreds of meters in every direction. While we, a user, occupies a very small fraction of the cell. So from an energy perspective, we're radiating broadly, covering a very broad area where we occupy a small section of that. That is highly inefficient way of communication. On the other side of the spectrum, if you look at fiber, where you take the energy and put it in a fiber that's very, very constrained, from an energy perspective, that's the most efficient way of communication. So as a general purpose in GreenTouch, we take these signals, wireless signals, and put them in fiber as fast as possible. That's one hint on how to solve these things. The next hint for wireless systems is instead of radiating in a very broad area, we want to focus that as much as possible. And so there's two ways of doing that. One, by taking antenna arrays and focusing the radiation power down to a single user. The other is to take these large cells and make them small cells. I'll go through both. So, like I said, you can have network topologies looking at small cells. You can have beamforming, spatial multiplexing. You can take a look at it from a resource management and scheduling and efficiency perspective, bandwidth allocation, and things like that. All of them are good, all of them are important, and all of them contribute to the technical problem. So let me take a few examples and then leave you with this. This is work that's going on inside of Green Touch today. Our first demonstration a couple years ago was what we called a large-scale antenna system. And this was, the concept is to take this radiation, which is broad across the cell, and focus it down onto the user. Steered beams and antenna arrays have been around for decades. There's nothing new there. But what is new is, well, all of that work focused on increasing the capacity of the system. Because if I focus the radiation on individual users, I can then reuse the resources again and again and again inside of the cell. So antenna systems, large-scale antenna systems with steered beams, have been used for capacity improvements. When you think about it from a power perspective, the radiation power is actually going down. So we're not focusing the beam to concentrate the radiation power and increase the signal-to-noise ratio and then go into higher-order modulations or whatever. We're keeping the signal-to-noise ratio the same. So the power is being reduced at the power amps and radios and things like that. So the fundamental question you have to ask is, as you reduce the power, does the noise and things like that actually increase? And so you get a plateau as I add more and more antennas, reducing the overall power of each of the elements. Does the noise figure of the receivers and things like that limit the performance? Or can I continue to use antennas to increase the spectral efficiency indefinitely? That's the fundamental question we asked ourselves. And we did this through a demonstration that we announced last year. And the results are shown here, going from 1 to 16 elements. We've extended it beyond that as well. And you can see that from a power efficiency perspective, we continue to plot with the number of elements. And so we think that we can use this technique actually to go all the way out to 1,000 elements and improve the power efficiency by a factor of 1,000. So this is one technique that you can use to achieve this goal. Of course, then this antenna array would grow to a huge antenna array. So from a practicality perspective, it's a challenge. But as I've shown here on this graph, we don't have to co-locate all of the antenna elements. We can distribute them among many, many different base stations. And this highly distributed system is actually one of the next generation wireless architectures that's being studied by Green Touch and others. So up to this point, we've focused on cellular architectures where you can reuse the resources again and again, and then pay attention to the interfaces. But in this case, you can remove the cellular structure altogether and think about these things as large-scale distributed systems and energy harvesting and whatnot. Of course, when you do this kind of processing, the processing requirements go up significantly. And therefore, we have to think about this from an algorithmic point of view. So I've shown here a graph, energy efficiency, again on the y-axis, spectral efficiency on the x-axis. And of course, the spectral efficiency increases as I increase the number of antennas, shown by the red curves, from the number of antennas from 100 to 1,000. And then, of course, the computational requirements in gigaflops on the y-axis. So if I increase the number of antennas to 1,000 to achieve my energy efficiency goal, but my power requirements remain very high, from an energy efficiency perspective, I get marginal benefits. So from a mathematics perspective, we want algorithms that allow us to expand in the antenna space, but using computationally less and less power. So there's a tremendous opportunity in low complexity algorithms. Whether it's low density parity codes or all these different kind of techniques low complexity systems are going to be important, because then we can increase the spectral efficiency and decrease the computational requirements overall. Small cells is another technique to limit the radiation. Small cells, again, have been used to increase the capacity, and cell splitting is a conventional approach to increasing the capacity of wireless systems and has been used for decades. One of the fundamental problems of cell splitting is, of course, the interface between cells increases proportionally to the overall system. And as a result, the system performance now is dominated by the edge as we go smaller and smaller because of the interference. And it's even worse than that, because in practical systems, operators and whatnot want to design their systems that overlap a lot, because they don't want consumers like ourselves to drop the call or drop the session as you go over the edge. Of course, as the cells become smaller and the mobility stays high, then there's a whole sort of control problem, because now you're changing cells much more rapidly as well. So from an operational perspective, small cells has challenges. But from an efficiency perspective, it's very good, because it allows us to, again, reduce the overall radiation and increase the cell, or increase the user footprint to the overall cell footprint. Now, of course, if we think about it and say, okay, that's great, we're going to increase the number of cells by a factor of 1,000, if we don't look at the cells carefully, we can actually increase the energy required. Think about it. If we took DSL modems or cable modems and multiplied it by a factor of 1,000, the energy, overall energy footprint would go up. So it's small cells not just by themselves. And I've shown that here with the curve on the right. Curve on the right has percentage gain in terms of power efficiency on the x-axis and throughput on the on the y-axis and throughput on the x-axis. So with low throughput systems, so the cells, you've deployed all of these small cells, but they're underutilized. Because the throughput is small, you have all this capacity, and they're underutilized. You actually pay a penalty for small cells. The efficiency gain is negative. As you increase the throughput, then the cells are occupied, fully utilized, and of course then the energy efficiency is a gain, net positive. So thinking about small cells, you have to think about the throughput as well. The way to get around this for generic throughput is to have small cells from a deployment perspective, but then focus the problem and the research on a network utilization. Power off the cells that are not used. Being able to provide coverage and things, dynamically modulating the cell performance to accommodate the network throughput. We call this, power following load. It happens naturally in high throughput small cell systems, but you can do it dynamically. When there's low throughput, you turn off a lot of small cells. And when it's high throughput, you turn on the small cells. This leads to a whole dynamic that our industry has yet faced. These networks are typically static, so now we're adding dynamics to these things. But nevertheless, once you have power follow load, you can start to get tremendous gains. And in fact, this was demonstrated last week. As I said, we had the pond result. PON is another one where you're processing a lot of data, in this case 10 gigabits per second,